This is Dr. Carroll, and this video is about circuits. So we've been talking about graphs, we've been talking about graph applications, and now we're going to talk about circuits and how that applies. Now remember that a circuit is a type of cycle. Remember, cycles begin and end at the same vertex. At least that's how we're defining them here. Okay? And so circuits then begin and end at the same vertex, and they either, one, visit every edge once and only once, or two, they visit every vertex once and only once. Now, the visit every edge kind are called Euler circuits, and the kind that visit every vertex once are called Hamilton or Hamiltonian. And so you can remember E for edge, Euler. That's one way you can remember. Euler is visit every edge. Hamilton, HV. Good luck on that one. Let's talk about Euler circuits. In the 1700s, there were two islands that were connected with 7 bridges in a town in Russia, or at least present-day Russia. And I have a visual here. Okay, so we have this island, and we have these bridges here, and they're connected. And the great minds of the day wondered, is it possible to cross every bridge once and only once and end up where you started? So could we start at one place, cross every bridge once and only once, and get back to where we started? Is that possible? Is there a path that would allow for it? And we can represent this as a graph where the land masses are vertices and the bridges represent edges. And so then we have our 4 land masses, and they're connected by 7 bridges or 7 edges here. And that's how we can frame the problem to be able to talk about it more intelligently, apply algorithms to solve it. Well, Euler came up with the answer, and that is if every vertex has an even number of edges, then yes, there is a path. So for the bridges in that city, it wasn't possible. Not every vertex, in fact, none of the vertices here have an even number of edges, okay, coming out of it, the degree of the edge. So let's explore what Euler came up with a little bit more. So if we had 3 vertices here, they're connected, okay? There is a path. You could start at A, go to B, go to C, and then come back to A. There's an Euler path. Now, if we add in another vertex here, how are we going to add it in such that, and we can't change this graph, where are we going to place an edge that would allow us to be able to do it? Could we put an edge from A to D? No, that won't allow us to get there. From B to D, well, same thing, it's symmetrical. There is not a way to add in just one edge here to get to D to be able to complete it with an Euler circuit. Okay, hopefully that helps to build your intuition about that. And another point is each vertex must have an even number of degrees, because for every vertex we need to approach that vertex and we need to leave that vertex. Approach a vertex, leave that vertex. So it has to have an even number. Now we might do that multiple times, but we need to take a unique edge each time. So that's why it needs to have an even number of vertices for each edge. So let's talk about an algorithm to be able to calculate an Euler circuit. Well, extremely common algorithm is a depth-first search, but with modifications, because otherwise it wouldn't work. So with depth-first search, we mark the vertices as queued or visited, but now we're going to mark the edges as visited or used instead of the vertices. Now this is going to cause some cycles, and that's okay. That's what we're looking for. We want it to cause some cycles. But it's going to cause some cycles prematurely, especially if we favor vertices in a sorted order, the lowest value being first. So after we complete a cycle, Then we'll do another depth first search, again with modification that we're marking the edges instead of the vertices. And then with these 2 cycles, and we'll start at the first vertex in the path of that first cycle that has an unused edge and explore that path. And then we'll join this cycle into the first cycle, and then as you can imagine, we're going to repeat. Let's see an example. Okay, so here we have a graph. And on this graph, we have a number of vertices and edges. Can we have an Euler path? How do you know? Well, you could 1, test it and see if you can come up with one. Or 2, you can count the number of the degree of each node. Well, this one has a degree of 4, 4, 2, 4, 4, 2, and 4. Every vertice has an even degree, even number of edges, so we can have an Euler path. Let's start at A. So if we do a depth first search, we're going to go to B first, and we're going to mark the edge between A and B as used. Mark the edge. We're going to go to C, we're going to go to D, and we're marking the edges with red to indicate that they've been used. We're going to go to G, and then we're going to go back to C because we're not marking vertices as used, we're marking edges. And we're going with the smallest vertex label first. So then from C, we only have one option. We're going to go to F. F, we have several, but we're going to choose to go to B. And then from B, we only have one edge that's not used. We're going to go to E. And E has a couple options, but we're going to favor A because it's of lower value. Okay, great. We completed an Euler circuit, except we haven't used all of the edges in the graph. So what we're going to do is we're going to go to the first vertex in our path, and that would be F, that has an unused edge. Oh, G is the first one. So we're going to go to G, and we're going to look and we're say, okay, now we're going to mark this edge as red, and we're going to include it. And then we're going to mark this edge as red, and then we're going to mark this edge and then used. So what we've done is we've taken the path that was A, B, C, D, G, C, F, B, E, A, which is an Euler circuit. And we've said, okay, well at G here, we're just going to make this appendage here. So instead of going D, G, C, etc., we're going to go D, G, E, F, G, then continue on. See how we took the 2 cycles and we merged them. So we created a little bubble, if you will, off of the previous path, and that completes our Euler circuit. Okay? Now let's look at our island problem here. So does this have an Euler path? We already talked about it. It doesn't because they don't have an even number of vertices. But let's just, for fun, start. So if we started A to B, and then B to C, C to D, and then we'd come back to A, well, we started at the same vertex we went to, but we didn't visit every edge once. So let's continue. We would go A to B, B to C, but then we're trapped. There's only one edge that isn't used at this point, but we've used all the edges from C. So just to illustrate how that isn't possible there. So that's Euler circuits. Now let's talk about Hamilton circuits. A Hamilton circuit, remember, is we're going to visit every vertex once and only once and end back up at the original vertex. This is exemplified by the classic computer science problem, traveling salesman. And the problem for a weighted graph is to find the optimal route to visit every city vertex once and only once. That sounds just like a Hamilton circuit. So let's imagine that you are considering graduate schools. And so you've come up with a list of some of the best graduate schools in the nation, and you're over break, you're going to visit them. And so you're trying to be efficient because it's going to cost a lot of gas money to visit them all. And so you have this path here. And you're going to start at MTSU, and you're going to hit up Brigham Young University. Woohoo, go Cougars. And then Carnegie Mellon, then Stanford, then MIT, that school, and then University of California, Berkeley, and then Urbana-Champaign, and then back home. Woo! And that will run you 14,000 miles. Well, guess what? It turns out with Hamilton circuits, unlike Euler circuits, there's not a clear-cut, efficient way to process, to be able to come up with the optimal route. And so that opens up to a whole class of problems called NP-complete problems. And we're not going to get into that today, but this would be an example of a Hamilton circuit. And just to show you, this is not the best route. We're at 14,875. Well, what if we moved up going to the MIT school, and then we did Carnegie Mellon next, and then we hit up BYU. Oh, then we need to stop by Illinois, then BYU, then go out to California, and then come back. Woo! Down to 6,700. Now you might be able to do a little better than that, but by and large, we've improved, and this is a Hamilton circuit. Okay, we visit every vertex, all these schools, and once and only once, and we got back to where we ended. That's the video for today.